So it's an introduction to deep learning. And we're very lucky to have it from Camille Legault. Camille has been part of our team, AI Launch Lab, and prior to that, Artificial Intelligence Concordia since 2018. And had a big role to play in terms of the development of the organization and kind of the value that we wanted to provide. So Camille is an AI project lead, and he has a master's degree in machine learning at the University of Montreal. And previously he was an applied research scientist intern at Element AI. And there's a lot more to say about him, but we can leave it with that. Camille, do we have you?
I'm here, yes.
Cool. Let's get you up here. Cool. So I guess, yeah, take it away whenever you're ready.
Yeah, so I guess we'll get started. I'll share my screen. So the way I prepared this workshop is really just, I made a Colab notebook and we're going to go through it together essentially. So I can post the link. I don't know if I made it shareable. Sorry about this. All right, so I will just share the link. You can follow along. You can look at the screen. Good, now I don't see the chat anymore. Why does it do that? Oh, sorry about that. Yes, all right, let's get back to it. Sorry about this. So yeah, so I don't know exactly how many people here are familiar with PyTorch. The idea here is like I wanted to teach you, you folks how to use PyTorch to do deep learning essentially. And I really won't have time to much, like we only have half an hour, like I'm not gonna get into any of the theory at all. So if that's what you're interested in, it's probably the wrong workshop for you, but I really recommend there's a course by Yann LeCun online. The deep learning book is also still relevant. I know it's from 2015, but I think it's still good to read through. There's a lot of good information about the intuition behind CNN, RNNs, and all that, early models. So first, before we get started, I don't know even if people are familiar with supervised versus unsupervised learning. But really briefly, like with supervised learning, what we're working with is actually pairs of input and output data. So a classical example of this is just, pictures of cats and dogs and their accompanying labels. So like in this case, cat. So that would be supervised. Unsupervised, we just don't have that label anymore. So we just have the initial data itself. So you can think of just the initial pile of cats and dogs. And so like what we could be trying to do is like maybe cluster it and try to see if maybe there's some features in the images themselves that allow us to find two clusters of cats and dogs. We could also, if we only had a data set of cat pictures, we could try to generate new cat pictures by learning the distribution of cat pictures and building a generative model. So that's also something we could be doing. So anyway, I won't really go into much more about unsupervised because we're not going to be doing that today. We're only going to be focusing on supervised learning. And really like the way I wanted to do this is really like we're going to start by doing just a simple linear regression in PyTorch. And then we're going to move on to a more like a feed-forward neural network in PyTorch as well. So
Camille, we know how everyone loves cat pictures. So that was a great intro. So
yeah, that was my personal choice. Yeah, so I think it's also a classical choice in deep learning these days to use cats and dogs. So yeah, so just briefly on PyTorch. So really when you're working with PyTorch, you're really looking at two main features. So you're looking at operation on tensors with GPU support. So it's a bit like NumPy, but with really GPU support, because that's kind of the main point of using PyTorch is like you're going to be running this on the GPU or TPU because the computations you're doing are quite intense. And also a mechanism for really computing the gradient, so like building computational graphs dynamically, and we call that, that system is called AutoGraph, and it does automatic differentiation. So really I wanted to maybe just briefly explain, maybe actually I'll get back to this after because I don't want to get too bogged down by this computational graph, but essentially in PyTorch, the way it knows how to calculate gradients is by dynamically creating this computational graph. So when you create tensors as inputs, they become leaves in this graph. So you can see here 5 and 15. And when you add any operations on those tensors, they're added as nodes in the graph, and they're connected to where they were called or what was given to them as input. And then in the end, you have the output, which is the root. And really, when you're trying to find the gradients, you're doing back propagation, you're really starting from the back and using that computational graph, trying to understand the relationship between the different nodes to know what the gradient should be. But we'll get back to that afterwards. So really with this, what we're trying to do here first for this linear regression is I created these dummy X and Y values here to really like just have a straight line of points. And we're going to be trying to learn just a line that goes through using linear regression. So really what I did here, I just created like a points 1 to 10 using here a list comprehension in Python. I'm not sure how familiar people are with Python here. Please, don't hesitate to use the chat if you don't understand something. What is the main difference between PyTorch and TensorFlow? Maybe I'll leave that one to the end, but really like, actually these days, there isn't that much more differences. It used to be that PyTorch was like the dynamic, it was mainly in the computational graph aspect. So it used to be that TensorFlow, you had to manually define your graph and say like, oh, this node is connected to this, and then we're gonna be running the data this way. And then PyTorch was really more dynamic, as you'll see in the code examples. But honestly, these days, there's very little difference between PyTorch and TensorFlow. I would actually say the biggest difference these days is that with TensorFlow, you have Keras. So Keras, we're not covering it today, but it's a really, really simple way of building models and training them. So I would say that today, that's the biggest difference in my opinion. But 2 years ago, it was completely different. So to get back to the example, so I just created these points, 1 to 10, using here list comprehension in Python. I'm converting it to a NumPy array for 2 reasons. One, because I want to have a column vector, and 2, because from a NumPy array, then it's pretty easy to convert to a PyTorch tensor. So what I'm doing here is I need to reshape this, because when I actually give, I don't know if I'm connected to the, yeah. So when I actually I'll comment this out. So if I just create a NumPy array from just a list, it's actually not really going to have the type of dimension I'm looking for. So if I look at the shape of this, I can see that we're actually just 11 and then comma, and then there's a dimension missing. So what I'm doing here is I'm really just doing the reshape to add that missing unit dimension here. So you can see now we have 11 times 1, so we have a true column vector. So I'm doing the same with the y values. I just picked this formula 2 times I plus 1 to get the y. No particular reason for that. That was just what I chose. And then we can plot these again. And so we see we have this plot. So now we'll be actually creating our model. So with PyTorch, really, when you're creating any new model, you really want to inherit from the torch.nn module, because that module has all of the autograd and every functionality you need to actually be doing backpropagation and optimization. So you inherit from that model. And then you also need to define just the init and foreign methods, really. You do need to call the super.init to be able to instantiate the base functionalities of the base model. And here, all I had to do for this linear regression, I just created one linear function. So using torch.linear, which is just a linear combination of the input and the weights. So just a quick reminder, I also don't know how people here are familiar with linear algebra, but really all we're doing here is really like we have an output y and an input x, and those two can have different sizes, which is why we have input and output size. And their relationship is through this W matrix and this bias B. So really that's what the torch.nn.linear function provides us. Sequentials is just a way of cascading multiple objects together. In this case, I only have one, so it's actually not necessary, but I put it there because I'm going to be using it in the next example. So I thought it was better to introduce it. It used to be that I remember like when I first was writing PyTorch code, I was cascading the input manually. So I was doing out, and then for the next layer, I was doing like is equal to something else again, and then I was passing it manually like that. But now with this sequential function, we don't have to do that. So it makes it pretty lightweight. Honestly, this code is like 4 lines long. So yeah, so as I said, we're just doing a linear regression. So we actually, our dimensions for input and output is just 1. So this example is definitely overkill for what PyTorch can do, but I think it gives a bit of the idea here. The learning rate, I'm just going to be using stochastic gradient descent. So the only hyperparameter I'm going to have here is going to be the learning rate of 0.01. Epochs, I guess, is also another hyperparameter, but I'm going to leave it to 100. I'm actually not going to be using GPU, but you could possibly use GPU. Yeah, so here is where I actually create, I see there's a lot of questions in the chat. Sorry, it's hard to monitor both at the same time. For everyone, okay. So I don't know what this question W. So W is really the weights of the matrix in the towards the and then the linear. So actually, like what you're not seeing here is that there are parameters behind this. So when you call this towards that and then that linear, it creates a linear layer, and it has parameters, but it's all in the background.
Sorry, Camille.
Yes.
Can you please go a little slow? Julie, the interpreter, is having a little difficult time.
Yes, I kept thinking about that, but I am not going slow. That's true. All right, I will go a lot slower.
Thanks.
Yes, okay. So moving on from that, so the last thing we need to define after having defined our linear regression model is the actual loss function. So here, because we are doing a regression, we're going to be using the mean squared error loss. And the mean square error is really just the difference between the actual value and the predicted value squared. So this is what we're going to be using. Also, part of the PyTorch library. The optimizer, as I said, will just be stochastic gradient descent. When you create the optimizer, you have to pass it the parameters that you're going to be optimizing or learning. So in this case, you just have to do model the parameters, and PyTorch will know how to fetch those parameters for you. And as I said, the only real hyperparameter we're going to be working with will be the learning rate here. So one thing you have to know with PyTorch that is different from something like Keras is that you have to define your training loop yourself. And that in a way is actually good because it gives you a lot more flexibility over what happens in that training loop, especially if you need to do any kind of debugging. In this case, we're not going to be doing debugging, but it's just something to keep in mind. So here, actually, what we're going to be doing is we're going to be doing gradient descent over the entire data set every epoch. So I'm going to be just creating a torch tensor, as I said, from the X and Y training points. And one thing you have to also do every time when you're building your training loop is you have to zero out the gradients in the optimizer. And the reason for that is very simple. It's just by default, PyTorch accumulates the gradients. This is for other types of models such as RNNs, but we're not doing that today. So we just have to zero out the gradients every epoch. By the way, an epoch, what it means is just a complete iteration of the data set. So, and typically you're doing multiple epochs when you're training a model. The number of epochs you're going to be doing is always going to be different depending on your data and your models. So it's in a way, it's a hyperparameter. So yeah, so the way to build this training loop is quite simple. So now that I have my inputs as a torch tensor, they are part of my computation graph, I can pass it to my instantiated models and get some outputs. Then from those outputs, again, it's pretty simple. I already have defined my loss function, this is going to be the root of my computation graph. So it's going to be at the end. So PyTorch is going to create this function here. It's, as I said, it's a mean squared error. So it's pretty straightforward. And so then I'm going to be calling this loss.backwards. And really what this loss.backward is really where the magic happens, I would say. So PyTorch will then, from the loss function and from the graph it's built so far, compute what the gradient is for each parameter. So each model parameter here. And then after this backward, this gradient will be stored in each parameter. There's a variable called grad. So if we were going through the parameters, we could call .grad and see what the gradient is. And then the last step is to use this optimizer to move forward in the optimization manifold. So I'm using a lot of jargon today. So this optimizer will use the optimizer we've defined here and the learning rate to know how to move forward. I don't know if there's questions yet. Yes, please go slow. I'm trying to go slow. Okay, so let's try to run this. I think it might take a while to run actually. No, actually, it's gonna be quick. So here we go. We can see here pretty easily that it learned it pretty much exactly learned what we wanted to learn. So it learned exactly the slope we needed to learn from the data points. So that's great. I mean, it's not really impressive because we know that PyTorch can do a lot more than this, but I hope that it gave you a bit of an idea on how to use PyTorch first. So now we'll actually be moving to a real feed-forward network. So the reason I started with this linear regression is really that the base, layer, the linear layer, is what you have in those feed-forward networks. The only difference is that, okay, you can stack linear layers, but if you're just stacking linear layers, your model is still going to be linear. So you need some kind of activation function that we call, or we also call them non-linearities, to make the model, to enable the model to learn non-linear decision boundaries. So typically that's what you do with these activation functions. In this specific example, I'm going to be only using the ReLU function, which is defined here. Now I don't see the chat anymore. Yeah, so the ReLU function is pretty easy to differentiate. One thing to note is that it is not a, strictly speaking, continuous function, so it technically doesn't have a derivative at zero, if you remember your calculus. But the fun thing with deep learning is that we often don't really worry about these imperfections, so it doesn't matter that it's not differentiable at zero. So what we're going to be doing in this example is we're going to be working with the CIFAR10 data set. So the CIFAR10 data set, I can CIFAR10. So the CIFAR10 data set is just, images of 32 by 32 pixels of 10 different categories. So they're pretty small, but I think it's going to be enough because we're not going to be training on GPUs for this specific workshop. So I think it's going to be good enough. So I'm just going to import all these things. So as I said, we're not going to be using GPUs. And so this time around, the model we're going to be defining is going to be a bit more complicated than the last one. So first of all, we're going to have a flattened layer. And the reason for this flattened layer is pretty simple. If you look at this diagram here, you can see that the input to a feed-forward network is still a column vector. And when we're working with images, it's a two-dimensional matrix, essentially, of pixels. Or three-dimensional as if you have colors, because there's one channel for each color, so 3. So what this flatten does is it concatenates everything into one singular column vector. So it's necessary to pass it to our network. And then we're going to have a linear layer. So as I said, so the CIFAR10 images are 32 by 32 pixels big, times 3, which is red, green, and blue channels. So this is going to be a linear layer. And then our output of that layer, we just picked at 64, could have been something else. Again, these values are typically like hyperparameters, and the way you choose them is usually through experimentation. And even the number of layers, like you could choose to have a lot more layers than this, but this is just what I picked for this example. And then we're going to end, so we're going to have the linear, we're going to have ReLU, we're going to have another linear, ReLU, linear. And then we're going to put 10 because we have 10 classes. And then we're just going to have a softmax in the end because what we're doing is we're doing a multi-class classification. So we have one of 10 classes we want to choose. And the softmax just ensures that because what we're actually predicting here is a probability for each class of being a specific class. And so the softmax just ensures that when you add up all these probabilities, it adds up to 1. Yeah, so this is what we have here. Can't see any more. Okay. Yes, so we're going to be using CIFAR10. So let me just call this. So the CIFAR10, thankfully, is already included in the PyTorch data sets. So I don't really have to worry about downloading it. I can just, I imported Torch Vision and I imported CIFAR10. also imported this data loader functionality from PyTorch because it makes it easier to cycle through batches. So what I will be doing here, one thing you have to do is it's important to have a transform to tensor, because the natural, data type of these CIFAR images are actually images. And to work with PyTorch, we have to convert it to tensor. So this is pretty straightforward, I guess, that we need to pass the 2-tensor transform. And then we're going to be working on a batch size of 10. That's another hyperparameter. It could be something else, but we're going to keep it batch size of 10. So you can see the classes are here. I just numbered them here just to be more obvious. And I also downloaded a version of the dataset without the 2-tensor transform, just to show you that we can go through the image and see like what they look like. See, I think that's an image of it's like some kind of bird. These images are really small. It's hard to see. I think this is a car. Yeah. So anyway, let's move on. So now we can declare. We've defined our model up here. So now we just have to instantiate it. And we also need to instantiate the loss function. So in the previous example, I was doing a regression. So I had a regression type of loss function. I had a mean squared error. Now in this case, because I'm doing a classification, that's not going to work. So I need a new type. I need a new loss function to be able to do this. And so the loss function I'm going to be doing here is just categorical cross entropy. So really all it does is that it tells me the distance between, these probabilities I have in the ground truth, which is certain. So that's why there's a 1. So yeah, that's what it is. The actual calculation is here, but I won't really get into it because I know I'm running a little bit out of time. Yeah, so we'll just define this Lex function. This time we're going to be using Atom as an optimizer. We could have used SGD, but we're going to use Atom. Atom is a bit more advanced optimizer. It has momentum. So, and it also has an adaptive learning rate. So the learning rate is going to change depending on where you are in the optimization. Yeah, so I can just instantiate that. And again, same kind of training loop. Really just, I'm getting a batch of 10 from the data loader. I'm zeroing out the gradients. I'm passing that batch as an input to the model, getting the output. And then I'm just calling backward and calling an optimizer. It's pretty, I think at this point, this training loop is pretty straightforward. So this might take a bit of time to, probably shouldn't have done this. Yeah, I should have run this before. Yeah, so while this run, maybe I'll check if there's any more questions. There's no questions. Okay, so the last thing we want to do once this is done, I'm just going to be calculating the accuracy of our trained model, because you'll see that the accuracy may not necessarily be that good. And that's kind of on purpose for now. Yeah, so here just to give you a brief primer on the accuracy. What I'm going to be doing here for the accuracy, I'm just going to use the Jacob distance. So I'm just going to be looking at how many predictions are actually the same as the label they were supposed to be, divided by the total amount of predictions. Yeah, and I'm going to be using the test data set here. So the CIFAR 10 from PyTorch also comes with a way of getting the trainer test. So you can, before I was specifying train to true, now I'm going to specify to false, which is going to give me the test data set. So it's actually going to take a while to, I think I'm just going to stop it here because I don't want to wait too long after it. So it's definitely going to be a stop. All right. So I should have trained a little bit. So we're going to define this. All right, and now we're gonna, I calculated the accuracy for each batch in the test loader. And now I'm just gonna be calculating the total mean of the accuracies. So we can see that this accuracy is not that good. It's 40%. I think there's a question. Is there a question? I have 10 more minutes. Okay. Yeah, so this accuracy is only 40%. And we can even have fun and we can try to look and see what the, what the predicted classes was. So for example, for this example, it seems like this was a bird, and I don't know what what the data set was for this one. I think it was also bird. So what you can do is you can use dataset.classes to see what the actual number here corresponds in terms of classes. So we can see that it was indeed a bird. So in this case, the model was correct. I'm sure there's an example where the model was not correct. Let's try a different one. This one, I don't even know what this is. I think this is a dog or cat. I think this is a cat. Let's see what the model predicted here. Predicted 0, which is an airplane. So we can see that the model definitely made a mistake here. And it made quite a few mistakes because we have a 40% accuracy. So anyway, I think I went maybe a little bit fast over all of this this notebook. I don't know if there's any question right now. By the way, there's a few. This model is really not perfect, and there's quite a few mistakes that I kind of made deliberately. And I'll kind of let you think about it, and I'll go over them in the next workshop, which will be on the CNNs. So I don't know if there's questions right now. If there's no question, I guess we're going to end it here. I don't know.